خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. Chapter 4 Introduction to Probability. Section 4.1 The Basics of Probability. Let us start by defining probability. Probability is the chance that a particular event will occur. The chance that a particular event will occur. The probability is a number between 0 and 1. So probability of any event E is always between 1 and 0. If the probability is 0, it means that the event will not occur. If the probability is 1, it means that the event will occur. So when I ask you about the probability and you say that it is 1, it means this event certainly will occur. For example, if we roll a die, you know the die has 6 faces, and on each face there is 1 point, 2 points, 3 points, number of points from 1 to 6. This is all the outcomes. If you roll a die, all the outcomes are here. Now, if I ask you a question, what is the roll a die? What is the probability that you get 7 points on the upper face?
0.
0, because you cannot get 7. What is the probability that you get a number between 1 and 6 on the upper face?
1.
In this case, you say 1, okay? Because, of course, you will get from 1 to 6. If I ask you any other question, the answer would be a number between 0 and 1. So the probability as a number between 0 and 1, it reflects the uncertainty of the event occurring. After that, we need to define what we mean by the sample space, and then we will define events. So before, we need to talk about what is the meaning of an experiment. In probability language, it is the process that produces the outcomes. So what was the experiment in this example? Rolling a die. That was the experiment. Rolling a die, and notice the upper face. The number of points appear on the upper face. That was the experiment. This experiment produces an outcome. What would be the outcome? The number of points could be 1, 2, 3, 4, 5, or 6. So these are the outcomes. A very simple experiment could be flip a coin once. Flip a coin once. When you flip a coin once, you have 2 possible outcomes, either head or tail. So in this case, if you flip a coin once, you could have head or tail. So you can write the sample space in this case. And by the way, the sample space is the set of all possible outcomes. Okay, the sample space, collection of all outcomes, or set of all possible outcomes that results from the experiment. And the experiment, the process that produces outcome, and a single outcome, okay, whose result cannot be predicted with certainty. When you flip a coin, you are not certain what would you get. You don't know whether you will get a head or a tail. But you are certain that you have only 2 outcomes, 2 possibilities, either head or tail. So the collection of all outcomes, we will call it the sample space. And we will write SS as an abbreviation for the sample space. So for flipping a coin, the sample space either H or T. flipping a coin once. Well, if we flip the coin twice or make two flips of the coin, then the first coin could be H or T. And if the first coin is H, the second could be also H or T. And if the first is T, tail, the second could be H or tail. So the sample space in this case would be H, H, which means this is a single outcome. H is a single outcome for this experiment because you are flipping the coin twice. So in the first flip, you will get H, and in the second, you get H. So this is a single outcome of this experiment. Another single outcome, HT, or TH, or TT. Here, HH, you can write HH here. Here, the first one head, the second one is tail. The first one is tail, the second one is head. Both are tails. So this is the set of all possible outcomes if you flip a coin twice. What if you flip a coin 3 times? Now, how many outcomes here? Here, once I have 2 outcomes. Okay. Here I have 4 outcomes. Why 4? Because the first coin 2 possibilities times the second coin 2 possibilities. So I have 2 to the power 2, or 4 outcomes. Now, if you flip a coin 3 times, okay, so the first coin, 2 possibilities, twice, head or tail. The second coin, head or tail. The third coin, head or tail. So you will have 8 different outcomes. And you can make a tree diagram like this. So you can continue here, another H and T, okay? Another H and T for each choice here. So you will get, for example, SS in this case. The first possibility would be H, H. In fact, you can start from here, from this sample space. The first outcome here is HH. So you can take HH and add H once and T another time. So from each outcome here, you will have 2 outcomes here. Then you have HT, so you can write HTH and HTT, and so on. So you will have 8 outcomes if you flip a coin 3 times. Let us take another example of sample space. The sales manager for the West Side Drive-In is interested in analyzing the sales of its 3 best-selling hamburgers. As part of this analysis, he might be interested in determining the sample space, all possible outcomes, for two randomly selected customers. Okay. So we will ask 2 customers, or we will record what 2 customers will buy, okay, from these different hamburgers. The experiment here, what is the experiment? The sale. And the item of interest is the product sold. Now, we need to define the possible outcomes for one trial, for one customer. If one customer asks, what are the possibilities? We have 3 possibilities, either hamburger, cheeseburger, or bacon burger. So for the first customer, H, C, and B, or you can call them E1, E2, E3. So this would be the sample space if single sale is made, okay, one customer. If you are going to consider 2 customers, then there are 2 sales. If the first sale is hamburger, the second sale could be hamburger, cheeseburger, or bacon burger. If the first sale is cheeseburger, the second could be also one of these three, and so on. So how many possible outcomes? 3 choices for the first sale times 3 choices for the second sale. So you will have 9 choices, 9 different outcomes in the sample space. This type of graphing, which I used here also, is called a tree diagram. So let us give an example about a tree diagram. Clearwater Research is involved in a project in which television viewers were asked whether they objected to hard liquor advertisements being shown on television. The analyst is interested in listing the sample space, using a tree diagram. When 3 viewers, so how many viewers this time? We will ask 3 viewers about whether they objected or not. So what is the experiment? We will interview 3 people, and this would be the question given to them. Okay, so we will make 3 trials. We will ask 3 people, and when we ask each one of them, this is the second step. You need to determine all the outcomes for a single trial. If you ask one of them the question, he will say either no or yes. So there are 2 possibilities for each trial. Now, if you are asking 3, so these are the 2 outcomes for a single trial. Now, what about 3 trials? You will get this tree diagram. So this is the first person. If he says no, the second could say no or yes. If the first and the second said no, the third could say no or yes. So you will have these possibilities. How many possibilities are there? There are 2 for the first person, 2 for the second person, 2 for the third person. So there are 8 outcomes in this experiment, and one single outcome would be, for example, no, no, yes. This would be a single outcome for the 3 trials. For this experiment, when we do 3 trials. Let us see some questions. If 2 customers are asked, so we will ask 2 customers to list their choices of ice cream flavor. There are 3 flavors: vanilla, let me call it V; chocolate, C; strawberry, let me call it S. List, or let us not use S because of the sample space. Let me call it W. Okay. List the sample space showing the possible outcomes. All right. You need to understand the experiment first. The experiment is we will ask 2 customers to list their choices of ice cream flavor. All right. Now think of a single outcome, single customer. One customer. If you ask one customer to list his choice, how many choices are there? There are 3 choices, either V, C, or W for the first customer. Okay, so there are 3 outcomes if one customer is asked. Now, for the second customer, there are another 3 choices. So for 2 customers, we will have 9 outcomes. If the first customer chooses vanilla, the second can choose vanilla, chocolate, or strawberry, and so on. For each choice of the first customer, the second can still have 3 choices. So the sample space in this case will consist of V, 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 C, vanilla for the first, strawberry for the second, and so on. Okay, you can write all the 9 possible outcomes of this experiment. Another question. It's a sunny day and Cecilia goes to a cave to purchase an ice cream. In terms of size, she has 3 choices. Let me call this S, medium, large. For each size she chooses, she may include 1 topping of chocolate chips, let me call it C, wild strawberry, W, or almond flakes. Okay. So for each size, there are 3 choices of flavors if you want. By using a tree diagram, help Cecilia determine how many different choices of ice cream she has. You have to think first of the experiment. What is the experiment? Cecilia will choose the size of the ice cream, and then she will choose the flavor. And that's the experiment. Okay. How to find the outcomes? If she chooses first the size, what are the possible sizes? S, M, or L. So there are 3 possible sizes. And then there are 3 possible flavors. So she will has 9 choices. What are the choices? She could ask small chocolate chips, or small wild strawberry, or small almond flakes, okay, or medium of all of these 3, or large size of any of these 3. So you have 9 possibilities, and you can write all of them here. Another example, one automobile dealership sells Buick Cadillac, let me say B, C, D, okay, because Cadillac and Chevrolet starts with C, so let me say this is D, and this is V, automobiles. It also sells, so there is another type of cars, which is used cars. Please close the mic. Used cars. It also sells used cars that it gets as trade-ins on new car purchases. How many cars are sold? 2 cars. So understand the experiment. 2 cars will be sold, and these are the 4 different types this dealership sells. What is the sample space for the type of cars? 2 cars. The first car, how many choices are there for the first car? 4. How many choices are there for the second car? 4. So how many outcomes would be in this experiment? Of this experiment, 16. So if you want to use a tree diagram, the first car could be B, D, V, or it could be a used car. If the first car sold is B, the second could be B, D, V, or a used car, and so on for each one of these. And the sample space would consist of B, B, or B, D, and so on. You can list all the 16 possibilities in this case. The next point is the event. What is an event? It's a collection of outcomes. Not all possible outcomes, like the sample space, but it's a collection of outcomes. So in fact, it's a subset. It's a subset of sample space. And this subset could have one event, one outcome, and in this case we call it simple events, or more than one outcome, and we call it compound event. So for example, if you want to define an event from here, you can say the event E, where used cars are sold. UU only. This is one outcome. This is a sample event. This is a sample event. Okay. If you take more than outcome, then it would be a compound event. Okay. This has nothing to do with the question. Example, the KPMG accounting firm is interested in the sample space for an audit experiment in which the outcome of interest is the audit's completion status. The sample space is the list of all possible, of course. This is the definition of the sample space. The accounting firm is also interested in specifying the outcomes that make up an event of interest. So we need to find the sample space and to determine an event of interest. Let us see what is the experiment first. The experiment, 2 chosen audits. Okay, we will choose 2 audits. Okay, we need to understand for a single audit, for one audit, what are the possible outcomes? Well, for a single audit we have 3 possibilities: done early, done on time, or done late. So now we need to do this for 2 audits. There are 3 possibilities for the first audit and 3 possibilities for the second. So there will be 9 possibilities for doing these 2 or choosing the 2 audits. The first one could be early, and the second one could be any of these 3. If the first one is on time, also again I have 3 possibilities for the second, and the same for the last possibility. Okay, so I have 9 choices. So what would be the sample space? All of these from E1 to E9, 9 choices, 9 outcomes. Well, we need to define an interest here, an event of interest. What is the event of interest? At least one audit is completed late. At least one means 1 or 2. When I say at least 1 or 2. Why 2? Because we have only 2 audits. So at least one or 2 is composed. The event of interest is composed of all the outcomes in which 1 or more audits are late. So let us go here. The first outcome, early. Is this included? Are we interested in this event? In this outcome? No, we are not interested in this outcome because both are early. We need one at least to be late. Early on time, we are not interested. Early, late, yes. 1 late. On time, early, no. On time, no. On time, late, yes. 1 late. Late, early, yes. Late on time, yes. Late, yes. So 1 late or 2 late. So 5 outcomes should be there. And these are the 5 outcomes. So this is the event that we are interested in. Okay. It has 5 outcomes. The last point would be the definition of mutually exclusive events. 2 events are mutually exclusive if they have nothing in common. Okay, if the occurrence of one event precludes the occurrence of the other event. Precludes means prevents. Okay, prevents. So happening or occurrence of one event will prevent the occurrence of the second event, the other event. They cannot happen at the same time. So they are like disjoint sets. Nothing in common between them. They have nothing in common, no common elements. Okay, never intersect. This is what we mean by mutually exclusive. For example, set of all odd integers, set of all even integers. Here we have 1, 3, 5, and so on. Here we have 2, 4, 6, and so on. No number in common, no integer in common. So these 2 sets are mutually exclusive. So remember the definition. And let us take an example. In the previous example of KPMG, we talked about this event, which is at least one of the two audits is late. And now we need to define a second event. Neither audit is late. Neither audit is late means early. We need no late. Neither late means no late. Early or early on time early or on time. So we will take E1, E2, E4, and E5. In fact, we are taking all the outcomes that are not in E1. So E1 and E2 are mutually exclusive because if E1 occurs, E2 cannot occur. If one of them is late, you cannot have neither is late. خلاص, one of them is late. You cannot have this one. So this is the meaning of the two outcomes are mutually exclusive. Let us end by another example about mutually exclusive. Contract works does assembly work for high-tech companies. Each item produced on the assembly line can be thought of an experimental trial. The managers at this facility can analyze their process to determine whether the events of interest are mutually exclusive. Okay. What is the experiment? Producing a part on an assembly line. What are the outcomes for a single trial? Well, when you produce a part, it could be good or defective. Okay, how many trials are there? 2 products will be produced. If 2 products or 2 trials, then if the first is good, the second could be good or defective. And if the first is defective, the second could be good or defective. There are 2 possibilities for the first, 2 possibilities for the second. So we will have 4 outcomes, E1, E2, E3, E4. Now, let us define 2 events. E1, both products produced are good. So we have good. Event E2, at least one product is defective. So either one is defective or 2 are defective. So we will have E2, E3, E4. You can again see that these 2 events are mutually exclusive because if both are good, then no one of them is defective. I stop here, and inshallah next time we continue this section, and I open the floor for the questions.